Do you want to learn the basics of balance in chemical equations? This is what we will try to do in this video. We should start by defining what is a chemical equation. A chemical equation is an equation used to describe a chemical reaction, stating the elements involved in the reaction. An example of a chemical reaction is the flame that you have in a burner, a boiler or a gas kitchen. In this case, methane, the gas, is reacting with oxygen and produces carbon dioxide and water. However, this wording is the little used to a chemist. A chemist needs an equation that indicates the atoms involved in the reaction and their proportions. In this case, a chemist will write CH4 plus 2O2, arrow, CO2 plus 2H2O, meaning that one molecule of methane reacts with 2 molecules of oxygen to give 1 molecule of carbon dioxide gas, and 2 molecules of water. With this information, we can use the chemical reaction for further applications. But, how does a chemist know how many molecules or each component are? Well, this is what we call balancing the equation, and it is what we are going to do here. To understand what we are talking about, let's make some definitions. I will use the example of the reaction of methane with oxygen that we have seen in the previous slide. Chemical equations are written left to right, the same way that we write. On the left, we have the reactants. These are the chemical species that are going to react. In our case, the reactants are methane and oxygen. It is followed by a right-pointing arrow. On the right, we have the products. These are what we are going to get. In our case, these are carbon dioxide and water. The numbers of molecules involved are indicated by numbers called coefficients. In our example, the coefficients are 1 for methane and carbon dioxide and 2 for oxygen and water. When the coefficient is 1, it is usually not written. Sometimes the physical states of the molecules are indicated in brackets. The state symbols are S for solid, L for liquid, G for gas, and a Q for aqueous solution. Water is usually in liquid form, but in the example is gas due to the temperature generated. To balance a chemical equation is to determine the coefficients of each chemical entity in the equation. This is what we are going to do. There are two methods, the traditional method and the algebraic method. We will start with the traditional method. The steps in the traditional method are, first, write down each formula of each substance involved in the equation. In some cases, they are given. If not, ensure that the formulas are correct. Second, bear in mind that the final number of each atom in the reactants and in the products should be the same. Third, identify the most complex substance that appears in only one reactant and in only one product, if possible, and adjust the coefficients to ensure that the same number of atoms are on both sides of the equation. Fourth, continue balancing the equation, leaving the simple atoms at the end. Fifth, coefficients can be written as simple fractions. If you want to remove fractions, multiply the whole equation for an adequate number to make them whole numbers. To explain the traditional method, we are going to use the reaction of glucose and oxygen to produce carbon dioxide. The most complex molecule is glucose. Therefore, we assign the arbitrary number 1 to the glucose. We don't need to write 1, but to make it clear, I write it in this exercise. With the glucose fixed, we are checking the atoms of this molecule in the products. We start with the carbon. One molecule of glucose has 6 carbons. Carbon does not appear in any other reactant. In the products, carbon appears only in the carbon dioxide. Each molecule of carbon dioxide has 1 carbon. As we have 6 atoms of carbon from the glucose, we need 6 molecules of carbon dioxide. With 1 molecule of glucose and 6 molecules of carbon dioxide, we have the atoms of carbon balanced. We are checking the hydrogen. In the reactant, the hydrogen appears only in the glucose. In the products, the hydrogen appears only in the water. As we have already fixed the molecules of glucose to 1, we should have 12 hydrogens in the reactants. As each molecule of water has 2 atoms of hydrogen, we need 6 molecules of water to balance the hydrogen. We only have the molecule of oxygen and the atoms of oxygen to adjust. In the reactant, we have 6 oxygens provided by the molecule of glucose and an unknown number of molecules of oxygen. In the products, we have 12 atoms of oxygen provided by 6 molecules of carbon dioxide and 6 atoms provided by 6 molecules of water. 12 plus 6 equals 18. Therefore, we have 18 atoms of oxygen in the products. As the glucose contributes with 6 atoms of oxygen, the molecule of oxygen needs to contribute with 12 atoms of oxygen to balance the equation. Each molecule of oxygen contributes with 2 atoms of oxygen, therefore we need 6 molecules of oxygen. We have the equation balanced, but we need to check it. We do it by counting the atoms in the products and in the reactants. If the equation is balanced, the numbers have to be equal. We start with the carbon. In the reactants, we have 6 carbons provided by 1 molecule of glucose. In the products, we have 6 carbons provided by the 6 molecules of carbon dioxide. Therefore, the atoms of carbon are balanced. We continue with the hydrogen. In the reactants, we have 12 hydrogens provided by 1 molecule of glucose. In the products, we have 6 molecules of water. As each molecule of water provides 2 atoms of hydrogens, the total contribution for the water is 12 hydrogens. Therefore, the atoms of hydrogen are balanced. Last, but not least, is the oxygen. In the reactants, we have 6 atoms from the molecule of glucose and 12 from the 6 molecules of oxygen. These give a total of 18. In the products, we have 12 oxygens from the 6 molecules of carbon dioxide and 6 from 6 molecules of water. These also give a total of 18. Therefore the oxygen is also balanced and the whole equation as well. The algebraic method consists in creating a set of simple equations. The steps are, first, write down each formula of each substance involved in the equation, as we did in the traditional method. Second, assign a letter for each coefficient in the chemical equation. Third, group the letters by atoms creating equations, making those that appear as reactants on one side and those of the products on the other. Fourth, assign a coefficient, letter, an arbitrary number, typically 1. Fifth, resolve the equations. We are going to solve the same equation that we did for the traditional method, to check that both methods can lead to the same answer. In the equation, we assign a letter to each coefficient. Say A, for the glucose, B, for the oxygen, and so on. Now, we group the coefficients by atoms. For the carbon, in the reagents, we have 6 atoms for each molecule of glucose. As we have A, molecules of glucose, we have 6 times A, atoms. In the products, we have 1 carbon for each molecule of carbon dioxide. As we have C, molecules of carbon dioxide, we have C, atoms of carbon. We made 6 times A, equal to C. For the hydrogen, in the reagents, we have 12 atoms for each molecule of glucose. As we have A, molecules of glucose, we have 12 times A, atoms in the products. We have 2 hydrogens for each molecule of water. As we have D, molecules of water, we have 2 times D, of hydrogen. We made 12 times A, equal to 2 times D. For the oxygen, in the reagents, we have 6 atoms for each molecule of glucose and 2 atoms for each molecule of oxygen. As we have A, molecules of glucose, and B, molecules of oxygen, we have 6 times A, plus 2 times B, atoms of oxygen for reagents. In the products, we have 2 oxygens for each molecule of carbon dioxide and 1 for each molecule of water. As we have C, molecules of carbon dioxide and D, molecules of water, we have 2 times C, plus D, atoms of oxygen in the products. We made equal the atoms of oxygen in reactants and products. This means, 6 times A, plus 2 times B, equal to 2 times C, plus D. We fix A, to 1. You can fix any other letter to any other number. At the end, you should have equivalent answers. With the value of A, equal to 1, we check the equation of the carbon. We have that 6 times A, equal to C. As A, is equal to 1, we have that 6 times 1 is equal to C. Therefore, C, is equal to 6. We can find the value of D, using the equation for the hydrogen. We have that 12 times A, is equal to 2 times D. As A, is 1, we have 12 is equal to 2 times D. Or that D is equal to 6. Finally, we have to find B, from the equation of the oxygen. We have that 6 times A, plus 2 times B, is equal to 2 times C, plus D. Replacing A, C and D for the values that we already have, we get that 6 plus 2 times B, is equal to 18. Therefore, B is 6. Putting all together, we have the same equation as using the traditional method. And the number of atoms in reactants and products is the same. You can check it by following the same steps as in the traditional method. I hope that this video has helped you with an introduction to balancing chemical equations. The best way to learn them is by practicing, so, I leave below a link to my webpage, where you can find examples to practice. The exercises are resolved step by step. It is free and you don't need to register. As I'm planning to carry on uploading more videos and expanding my website, if you have any questions or would like to see any other chemistry-related topic, please, leave a comment here or on my webpage, as it will help me to help other people. If you liked this video, please click like, as it will help me to continue uploading videos. Thank you very much for your attention and I wish that you have a very good day.